So that's why I have kept it more and more basic things. A lot of things you will see that is just like what you are studying in your book. And then you will feel, yes, how these things are really applicable and useful to the society. And what main things here that we have to understand first. Okay. So some of the materials, because the functional nanomaterials, it's not only one or one kind of material. There are a lot of materials, but I have limited in this lecture. We are limited to only few, like noble metals, metal oxides, particularly titanium dioxide. And if we make a composite of these materials, then how they are beneficial and what are the changes. Okay, so mainly we'll discuss about metal nanoparticles, metal oxides, their composites, and some of the properties. And these are very basic things. We have learned a lot about these things. Only the thing that for the PG students, they don't know how they are applicable in the society and what are the things. So let's start with the functional nanomaterials. So what is functional nanomaterial? What are these nanomaterials and why we say functional? So generally a class of materials which are specified based on, or we can say like they have some extraordinary properties, but that is based on their size. There is a fixed size regime. That is not the bulk, but as compared to the bulk, they show some extraordinary properties, we can say. So as I already told, functional nanomaterials means it's not one kind of material, but it depends on the size and some extraordinary properties. So it means there may be many materials, functional nanomaterial, but something is common, that is the size. And at this size, their properties means again not a single properties, but based on the material, which kind of material it is, conducting, semiconducting, which kind of material it is, based on that, their properties, there may be magnetic material. So at that size regime, these materials, they show very different properties, electrical, optical, means all kind of properties. These properties are different as compared to their bulk counterparts. And when these materials are used for any either scientific or any real application, they show great enhancement, or the efficiency of those tools, those devices are greatly enhanced. So the main thing is what? The size regime. That we have to understand first. The functionality will come because of this size. So we have to understand what this size regime is. So this is normally we say nano size. So we should also understand what is this nano size and why these properties of this functional nano enhanced at this size. So the next slides we are going to discuss the nano size. And at this size means what is the properties? Why the properties are enhanced? All these different kind of properties which are mentioned here. So we have to understand what is nano, or we have read many times nanoparticles. So what is called nanoparticles? Why they are so important? And what is the difference at this size? Or simply we nowadays in news, in papers, everywhere, we generally find always these two words, nanoscience and nanotechnology. So how we define these things? Okay. So we know nano, known to everybody, the dimension. But the size between 1 to 100 nanometer. At this size, generally, these materials show very different properties. So only nano is something, but there is a range. If you think about 1 to 100 nanometer size of anything, what it means. So if you consider, or if you think that an individual atom, what is the size? So it's in angstrom. So it means if you talk about 1 nanometer, 2 nanometer, or 100 nanometer, it means there are number of atoms. But still, we say like limited up to 1 to 100 nanometer. So the nanoparticle, what we listen always, nanoparticles, it means few hundreds of atoms. So generally the nano or nanoparticle, nano-dimensional particle, whatever we can define. The word nano means the size ranging from 1 to 100 nanometer. Generally, we talk about the nanoparticle and they are called spherical, but there may be size variation also. We'll see in the next slides. But very important thing is that at this size, what about the surface area to volume ratio? So first we'll see this, because generally we always listen that at lower size or nano size surface area is greater, but how? Because I also interact with the PhD and PG students, and many times I found that we know the students, they know very well the surface area is decreased or increased when size is changing, but exactly how it matters, that sometimes they don't understand. So for example, suppose we have this cube. So if you find surface area and volume of this, considering the sides like 3, okay, just take 3, then find the surface area and volume, and then you see the ratio. Now if I decrease the size, in that case again you find the surface area and volume and see the ratio. Again if we decrease the size and then see the ratio surface to volume, 6. So as we decrease the size, what we find that the surface area to volume ratio is increased. So this is the beauty of nano. You can imagine when we have the size of nanometer or angstrom, then what will happen? The surface area to volume ratio will be increased a lot. For example, you see, in nanometer, from 1000 nanometer to 1 nanometer, if this is the size, then surface area to volume ratio increased 1000 times. So now you can understand the beauty of nano, that at this scale, the surface area enhanced how many times? So what we can say, that surface to volume ratio increases with decrease in particle size. Okay. Now, if we want to formulate this, then simply we can say that this is inversely proportional to the size, length, whatever it is, depends on the shape of your particle. For spherical particle, again the same thing. If you take any sphere of radius r, then the volume and surface, and then the ratio of those, you find the same. The ratio is inversely proportional to the radius. It means whatever the shape, main thing is the size. If size is decreasing, your surface area to volume ratio will be increased. So smaller the particle, greater will be the surface area to volume ratio. So what are the important things we learn here? That at this scale, at nano scale, the surface to volume ratio is very high, and because of that their surface properties is very different as compared to the bulk. So this is not only the reason that they are very fascinating and attracting, but if we go to the different properties, then we'll find, yes. So we'll see in next slides also something more what is important except this, or we can say along with the surface area. For example, in graduation, in PG, we always learn about the chemical reactions, and we have learned like catalyst. And in catalyst, we say that when we use the catalyst in powder form, the reaction accelerates, or rate of the reaction is very high. So what is the reason? The reason is the surface area. Because when we use these particles in powder form, so their size is reduced. In place of a surface, the bulk catalyst, if we are using the particle, then each particle is having surface area greater than the plane surface what you are using as a catalyst. So first you have one cube, suppose, and you are making your reaction on the surface. And second case, when we have nanoparticles, you see in a small volume surface area is too much. It means there is a more surface area for the reactants to be absorbed on the surface and to react and forming the product. So this is the reason when we talk about the catalyst in powder form. So this is one of the real examples that you do, or maybe you have realized when you do any experiment in the lab. So accordingly, these terms, nanoscience, nanotechnology, nanostructures, nanomaterials could be defined. So there is something common always, that the size should be between 1 to 100 nanometer. Because at this range, these properties are enhanced, which we discussed in the first slide. So now you will be able to define what is science, what is technology, or nanochemistry. Okay. Just to show you that we know a lot of things by name, but do we know by size also? Nowadays, the virus world everybody knows, and we always talk about the mask and these things. It should be like that. The corona will not go. So you can see the size, and you can imagine what should be the dimension of the pores in your mask if there are virus. So generally the range is something here. And by name you know many things, so you can realize the size. So it's not like that we don't know nanomaterials or nano size. We are aware of that. From +2 onwards, we learn about a lot of biological molecules. We know the name, but we don't know the size. So you can see we are well aware of nano size or nanomaterials. Now, how we classify nanomaterials? Just what we learn about the size and one of the important properties at the size. Now, how we classify? So, generally, based on the number of dimensions, like in 3 dimensions, we define it like 0 dimension, 1 dimension, 2 dimension, or 3 dimension. So 0 dimensional, when all the dimensions, if you talk about x, y, z, are within this range. When any one of the dimension is out of 1 to 100 nanometer, but still the 2 dimensions are in nanometer range. Similarly, 2 dimension, when 2 dimensions are out of 1 to 100 nanometer, but still 1 dimension is in nanometer. when all the dimensions are out of this range. Okay, so we define like what is 0 dimension, 1, 2 and 3 dimension with reference to nano. This is important because we are talking about the nano. Now again here something very important. In all these dimensions 0, 1 and 2, at least 1 or 2 dimensions are in nanometer. Why I am giving a stress to this? Because the next what we are going to see the topic that is related to this. Why it's important? If we think, do we know any 0, 1, 2 or 3 dimensional material? Yes, you are well aware of these things and it is in your course also. You have learned about the fullerenes, nanotubes, graphene, graphite. We are well aware of this. So these nanomaterials, this is just an example because you know this, just to make you realize that you are well aware of these dimensional nanomaterials. Of course, you have not done yourself, you have not synthesized these things, you have not handled all these materials, but you know very well. Out of these materials, we'll talk a little bit about graphene because this is one of the best nanomaterial is known for many applications, mainly in field of electronics because of its electrical properties, electronic properties. So I will mention in further slides something about this. And as I told that when we talk about the nanomaterials, it's not limited to one material like carbon-based material. All the examples are called carbon-based nanomaterials, but there may be metals, there may be semiconductors. So different kind of materials could be in the range of 1 to 100 nanometer, and they can be classified at 0, 1, 2 dimensional nanomaterials. Either it is metal nanoparticles or semiconductor or any other. So till now we learned what are nanostructures, their classifications, and what happens to them and why they are very fascinating at nano level because of their surface area to volume ratio. Now something more, what it is. That is the quantum confinement. In your quantum chemistry, quantum physics, you all have read about the quantum confinement. So how we deal with this quantum confinement when we do research? So generally quantum confinement effect, it is observed when the size of the particle is very small and comparable to the wavelength of electron, or simply if I say like few nanometer. So if you remember when I was giving a stress on the dimensional, either 1 or 2 dimensions are in nanometer. Suppose we talk about the 1 dimensional, then 1 dimension means at least the 2 dimensions are in nanometer range. The 1 dimension is out of nanometer range. So it means this quantum confinement would be there. In case of 2 dimensional, again, at least 1 dimension is in nanometer. So this quantum confinement would be there. Like in case of graphene, it's a 2 dimensional. So thickness is what? 1 atom thick. The graphene is known as 2 dimensional nanomaterial and 1 atom thick. So 1 atom thick means the size would be like in hardly 1 nanometer. But it should be in angstrom. So we see a little bit about the quantum confinement. So how it is related to your textbook. So I would like to show that when we have a bulk material, generally when you learn about the band theory, how the bands, conduction valence bands are formed. So that time you have learned about this, the energy levels. So in bulk material, energy levels are continuous. But when size is reduced, what we see? The discrete energy levels are formed. And quantum size effect at this, when there are only few atoms, because we are talking about only few nanometer, or 1 nanometer. So that time what will happen? There will be only few atoms. So in case when there are few atoms, then this effect comes. And you can see, if we have a bulk, we have valence conduction bands, there is some band gap energy. But this is the bulk, and that time these are the continuous energy levels. But when size comes to this, then you see what happened. Discrete energy levels are formed. And that time the band gap is not same like in case of the bulk material. And it gives the quantum size effect. So this is important. And how we correlate it? Any other thing that you know? So that is this expression. If you just recall, when you learn about a particle in a box, you got this expression. And there you are getting the various energy levels. Just we can correlate it, the energy level to the size. The particle in a box, energy level to the size. So when size is less, this energy is more. So it can be related with this. At this level, the change in the size will give us change in the band gap energy. It means at this size, just by tuning the size of your particle, we can tune the band gap energy. So okay, this much you have learned in your book. But how this is effective? How practically this is important? For that, we have another point, that this quantum size effect at nanometer level, so change in optical properties. How? So if you just recall again some other things like absorption and fluorescence emission. If you remember Jablonski diagram, and you know very well that electrons are excited, they go to singlet or triplet state and they come back. While coming back to the ground state, they release some energy, and that is called fluorescence, phosphorescence. So just correlating with that, the first with the size, and then this effect, what you know, absorption or fluorescence. So if we have particles of this size where we get the quantum size effect, then you can see if we have the particle size just starting from 1 or 2 nanometer up to few nanometers, then their absorption properties are different. And we know due to absorption of different wavelength of light only and the emission of that, we are getting the difference in colors. In winter, the different colors, the jacket, the sweaters you have, that is also kind of example of absorption and emission. Why red is red, why blue is blue. So you know that. So you can just see that at this stage, we can just tuning a little band gap or the size only, we can change this. If you remember, you have the television, the LEDs in your home, the screen is made of these quantum dots. How you see the variation in colors when you look the screen of your TV. So that is also the quantum effect. Or you can say the screen is made of these quantum crystals. Just for example, this is semiconductor quantum dots. You see only the size and the emission of the color. When you irradiate with a fixed wavelength of light and the emission comes, so that will be different because of the size, because of the size variation, because of the band gap. So what we came to know that at nano scale, the major factors that influence their properties, and that we say the functional nanomaterial, but because of this size effect. Okay, so these two properties, surface area to volume ratio, quantum size effect, so these are major points which make these materials very, very important. So the research is being carried out by researchers, by scientists to make more and more efficient materials. It's not like limited, whatever is done till now, research is finished. No. There is always a scope for finding new materials which can be used for the long term application, real application. So it was the introduction where we learned a functional material is defined by because of the nano dimension, and because of this nano dimension only, they have different properties, and these properties are better than their as compared to their bulk properties. Now we take example of some material and also we'll see some results. Most of the results what I have done myself, and also some of the results from other groups, just to realize you something what we are talking about, just to make your better understanding about the concept. Okay. So if you think about the noble metals, what are noble metals? Why they are important? So today, whoever are there, either from physics or chemistry background, so we define noble metals in a little bit different way. But especially this group elements are known as noble metal. Okay, we can define in different way. But the important here is nanoparticle. Noble metal, nanoparticle. So these noble metal nanoparticles, why nanoparticle I'm using? So just remember, whenever we talk about the nanoparticle means the size should be in the dimension 1 to 100 nanometer. Okay. So noble metals are there, but they are in form of nano or at nano scale. So what happens generally? At this nano scale, because of the nano scale, size or shape, both the things. So these particles, they show very dependent optical properties. Dependent means their shape and size dependent. And why? Because of the localized surface plasmon resonance property. So this is one of the special, we can say, a unique property shown by noble metals at nano scale. Just stick to the words, right? Localized surface plasmon resonance in noble metals at nanoscale size. And why it happens? Because of the collective oscillation of free electrons on their surface. We'll see also why. So collective oscillation of free electrons, we know if there are oscillation of free electrons, electromagnetic field generates. But the unique property of these noble metals, because the same phenomena will not be observed in case of semiconductor. So that's why it's unique property for the noble metals. They have selective photon absorption. Means the absorption property. Selective photon absorption, that also we'll see, and electric field enhancement. So these two property of noble metals at nanoscale are very important for them, and all kind of application what are mentioned here, these are due to this. So we have to understand these things. Okay, so they have a lot of application in many fields. It's not only what I have mentioned here, but when you read about little more on noble metals, you will see almost all domain of science you see how they apply and simply the application of it. What is mentioned here? Better to look in the next slide. This property, again, I'd like to mention that we have learned about the molecule. Okay.
I think there is a disturbance. Please, Anju. Please, Anju, can you listen me? Please keep your audio off. Anju, please keep your audio off. Okay. Jayaprakash sir. Jayaprakash sir. डॉक्टर शर्मा.
हाँ जी मनोज जी.
लगता है आवाज नहीं आ रही सर.
जस्ट ए मिनट, मैं बताता हूँ. मनोज जी. डॉक्टर मनोज. क्या
शर्मा सर.
मनोज जी.
हाँ जी सर.
मनोज जी,
सर
जयप्रकाश जी को बोलिए कि एक बार लीव करके दोबारा ज्वाइन करें.
हाँ 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 हाँ. सर मेरी भी बात हुई उनसे. वो कह रहे हैं कि 2-4 मिनट का टाइम चाहिए उनको. थोड़ा सा
कोई नहीं,
लगता है वहाँ भी शायद डिस्कनेक्शन हो गया है.
कोई नहीं.
हाँ
बस ये
ठीक
है
सर.
कि इतनी देर में बच्चे
पाँच
भाग जाएंगे.
दो नहीं 2-4 मिनट के अंदर सर आ रहे हैं वो. वैसे मैंने बात हुई
कोई
है
नहीं
मेरी.
सर, अंदर ही है, चिंता मत करिए.
हाँ जी ठीक है सर.
हाँ. बाबा की फोटो लगा रखी. सही में बताइए.
शर्मा जी, डॉक्टर शर्मा।
मनोज जी कर लिया सर ने ज्वाइन?
सर ऐसा है, उनको थोड़ा दिक्कत आ रही है। वो कहते हैं कि 5 मिनट तक है दिक्कत उनको।
कोई नहीं सर,
हाँ
आप स्टूडेंट कह दो कि वेट करें,
हाँ हाँ हाँ।
अनाउंस कर दो
तो
एक बार।
हाँ जी सर।
हाँ
सारे स्टूडेंट्स जो है ध्यान दो, थोड़ा सा दिक्कत आ गई है फ्रॉम द स्पीकर एंड। हम कोशिश कर रहे हैं थोड़ा सा दोबारा से कनेक्ट करने की, तो प्लीज वेट फॉर द 5 मिनट्स मोर।
Is it audible?
yeah, it's audible Jayaprakash ji.
Okay. Sorry, I'm very sorry.
Don't worry sir, you may
There was some
continue.
problem from my side itself.
नो प्रॉब्लम सर,
No problem sir, continue please.
प्लीज कंटिन्यू सर।
Okay, so we were here. So about this, what we just looked at this slide, the noble metal nanoparticles, and this absorption or the electric field enhancement, these things. Better we look at this theory, and based on this theory, that the absorption of the electromagnetic radiation in case of a nanoparticle it depends on many factors. So in last slide, we just look at the nanoscale, but there are other factors also. The wavelength of light, also the dielectric constant of the medium. So there are various factors that depends on the absorption properties. So if you look at the my theory, then you will understand something about the absorption at nanoscale. And a special thing that the resonance, what we know, where the absorption takes place, we know the visible light, the wavelength ranging from 400 to 800, between 400 and 800 nanometer. So definitely the things would happen at nanometer scale because the wavelength, the visible light, the wavelength of the visible light is ranging within nanometer. But because of some other factors, the nanoparticles within 1 to 100 nanometer, they interact with the visible light of wavelength between 400 to 800 nanometer. And that time, the absorption takes place. So you should look once what is this my theory and how it is related with the nanoparticle and the absorption. So we will not discuss too much because we don't have time to discuss a lot about that. But you can just look once that this theory you have learned in your graduation, in your master, and this theory is generally used here. So now the what properties we are talking about, the optical properties. So we can see that if we have particles of different shapes and size, their absorption properties could be tuned. Means we can have a filter of wavelength of light. Means for any size, suppose if we talk about the blue one, then it can absorb wavelength from 500 to 700, suppose. Then we can filter the other wavelengths. So this is one of the applications. How we can filter the wavelengths? We can use it. You know, many optical instruments where we filter the wavelengths. So this could be nanoparticle. If we have the nanoparticles, we can use for those purposes. The same, next, this is also same, the absorption properties, but here what we are looking that on the surface, there are some molecules. Right now we are talking about the application part, how these nanomaterials, these noble metal nanoparticles are being used. So here you can understand if we have the particles on the surface, any molecules, then what will happen? The dielectric of the medium will change. And because of that, the absorption will be changed. So this is called kind of sensing application. That if there is any molecule on the surface, that will change this absorption property and change. So this shift will tell us that there is something on the surface. So that will tell us kind of sensing. Okay, so many sensing devices you know, and that works on something on this principle. Not exactly only for noble metal, but this is one of the examples. Same if we put our nanoparticles, for example gold, in any medium and we vary the size, then also we'll see the change in the absorption property. So this only the UV visible spectra will tell us a lot of things wherever we are using our nanomaterial. Based on that, we can get a lot of information. So this is the kind of real application. Similarly, this is one of the area for the sensing. We were talking about the sensing. So now we come to the spectroscopy, which the Raman spectroscopy. Everybody has learned about the Raman scattering. And we know the Raman scattering, the yield is very less. If you have one or two molecules, then you will not get the Raman signal. But using these nanomaterials, especially the noble metals, what happens generally? It is surface science kind of sensitive technique where what happens if we have some molecules on the surface and if we irradiate with what? With a laser, and this laser can excite those plasmons, means the free electrons on the surface. So what it does, it excites the electrons, and because of that, the electromagnetic field that enhance on the surface, and because of that, the Raman scattering that enhance, and because of that, we get the spectra of that molecule, the Raman scattering, Raman spectra of that molecule, and based on the spectra that is well known, the vibrational frequencies for different bonds we know very well. So based on that, we can certify that which molecules are coming to the surface at this condition. So this is one of the sensing mechanism what I explained here. So noble metals are generally used for this kind of thing. And what is the very important thing here, that even the single molecules, when the single molecules could be detected. So if you think about the real application of this, that in water, any kind of impurity, in air, any kind of impurity could be detected using this. This is now kind of technique, surface and Raman scattering technique. I explained based on the Raman scattering what we learned in our class, but now it is a kind of technique. So using this technique, we can have sensing application, and not only the sensing, but also we can have a lot of information about the molecules, their vibrational properties, their structural informations, their interaction. We'll see in the next slides something about that. How local interaction will also tell us something about this. They are also being used for the DNA detection. And there, what is the main thing? The mechanism part is the electromagnetic enhancement. Because of the laser, the electrons are excited on the surface and they increase the electromagnetic enhancement on the surface, and that enhances the Raman scattering. So this is an example that we can create different kind of nanoparticles on the surface. So this is one of the example from my work, that we have created some particles on the surface. You see the elongated, then spherical, embedded. So this is one of the technique. By irradiating with the ions, we can create nanoparticles. And these nanoparticles, the optical properties means the absorption. Now the same the sensing, SCRS sensing application. You see, when we have the nanoparticles on the surface, this is the Raman spectra, okay, for methyl orange. And in this Raman spectra, it shows the different, you see the vibrations at 1590 centimeter inverse, it belongs to the benzene rings. This part that belongs to this. Okay, so when these molecules are interacting on the molecules, what we are getting, the enhancement on some of the peaks at some, like particular 1600 or at 1100. So what it shows? It shows the interaction of molecules, or you can say a particular part of the molecules on the metallic surface. That means the interaction, how molecules are interacting on the surface. That can also be found. So this is little bit about the noble metals, how we use these noble metals for applications. Now metal oxide. So if you think about the metal oxide, there are mainly TiO2, zinc oxide, and there are some other metal oxide which are used as a photocatalyst. So here I'm taking the example for the photocatalyst. And out of all that, TiO2. TiO2, जैसा कि हमने पहले पढ़ा है, we know very well that for semiconductor we have valence and conduction band, and there is a band gap. And when they are irradiated with the wavelength, means radiation of wavelength equals or greater than the difference between valence on the band gap, that what wavelength we need to excite these electrons. So this much we know in semiconductor. So if I say that for TiO2 the band gap is 3 or 3.2 electron volt, then we need, and this electron volt that is correspond to the UV light. means from I can say 200 to 300 nanometer, okay, in terms of the wavelength. So if you excite it with the wavelength between 200 to 300, so depending on the band gap, because there is a range 3 to 3.2, the electrons will excite. This must be known in semiconductor. But this is transparent for the visible light, because for visible light, the wavelength starts from 400 to 800 nanometer. So for UV light, this material is very useful. And how it is useful? That we'll see that these materials are generally used for photocatalytic application or antibacterial. So what happens generally? These electrons which jump from the valence to conduction band, these electrons, they interact with water molecules or oxygen molecules present in the air. Okay, and these electrons, when they interact with these species present in the air, they form some reactive oxygen species, free radical kind of molecules. So we can see in this video that when these radicals are formed, what they do, whenever they interact with any organic molecule, like the oxygen or water molecules which are present in the air in form of moisture, they form radicals. This kind of radicals or superoxides. And when these oxides, they react with organic molecules, any kind of organic molecules, they react with them and they convert them into CO2 or H2O. So this is the photocatalysis, generally what we know. So this TiO2 or ZNO or any such metal oxide nanomaterials, they are very, very useful in case of photocatalysis. And we can see we have very harmful organic molecules also present in the air or present in the water. So these metals are generally used for degrading those organic molecules. We learn about the SCRS, so these metals are also useful for the sensing application. Now we talk about the sunlight, and in sunlight what we know that sunlight is not fully only UV light. So if you want to use these materials for real practical application, how it is useful? Because the sunlight has only 5, even less than 5% UV. It means we must have material that can absorb or whose band gap lies between in visible or IR region. If the band gap is corresponding to the visible or IR region, then we can use the sunlight for exciting those electrons which are jumping from valence to conduction band. So the TiO2 or similar metal oxides are very useful, but they are active only in case of UV. So this is the drawback for them, we can see. They are useful only under UV light. So there is some strategy that we can make it visible light active material. And for that, there are some methods like doping, or we can make a composite with other materials to make it visible light. And so most of the application like photocatalytic, antibacterial, or the sensing application, in case of TiO2 or other metal oxide, similar metal oxide, only this is not sufficient because they can be active only under the UV light irradiation. That's why we need to modify this. And for modification, we do doping. This is one of the case. So again, this is that you know very well. For doping, we have different kind of doping, P-type or N-type doping. Okay, where we have holes or we have extra electrons. So when we do doping, what happens generally? The band gap of the semiconductor is modified. And P or N-type doping, generally what happens? Between this conduction and valence band, what happens? other energy states because of presence of electrons or holes. Energy states are created, and it reduces the band gap. And you know, when band gap will be reduced, means energy is reduced, then the wavelength will be increased. Means from UV to visible, the energy is inversely proportional to the wavelength. So if it is reduced, the wavelength will be higher. It means from UV to visible. This is the example for silicon, but in case of TiO2 or zinc oxide or any other metal oxide, what will happen? If band gap will be reduced, then what will happen? Any photon of less energy, means higher wavelength, can be used to excite these valence band electrons to conduction band. And more number of electrons means more number of radicals. Okay, those radicals, hydroxide radicals, superoxide radicals, and they will degrade more and more organic species. So in case of silicon, these dopings N-type, P-type, this is also very interesting. For example, we know very well about the silicon-based solar cell. So in silicon-based solar cell, what happens generally? N-type or P-type of silicon are used. So you know very well the dopings, but silicon-based solar cells you don't know. So just for giving example that how this is useful, because we know these things. Again, we come back to our topic, because we were mainly discussing about metal oxide or noble metals. So this is one of the example from the research that we have done. We have one-dimensional TiO2 nanofiber. You can see this is one-dimensional. The thickness, or we can say the diameter, would be in nanometer, but the length is in micron. So this is one-dimensional TiO2 nanofiber, and it has been doped with the tantalum. After doping, what we found that the band gap is reduced and photocatalytic. Again, these results, I think for PG students, it will be difficult to understand what it means. So I just tell you in the short that after doping, what happened? The band was organic molecules. And also this is useful for sensing. After doping, the sensing enhancement, you can see the Raman spectra, and after doping, there is enhancement in the signals, Raman signals. And this was because of the energy state created just below the conduction band, because of the doping of tantalum. So this is just an example that how doping is important or useful for tuning the band gap and also its function to enhance its functionality. Now what will happen if we mix these two? So we can go a little faster, because here very important was to understand about noble metal and metal oxide separately. Now we know their functionality. Only the difference that the noble metals, they are excited with UV light, visible light. Okay, visible light, and the metal oxide, they could be excited by UV light. Now when we combine these two, after combining, there are something more things like Schottky effect. If you remember, Schottky effect also we have learned in physics, especially at the interface of metal and semiconductor. So this Schottky effect, it works as a trap center that trap the electrons. So generally, when we use the UV light, the electrons are excited, okay, and then the trap center, what we talk about, because of this, the electrons don't recombine with the holes. So more and more electrons are available for what? For the degradation, for the photocatalysis. This is the one part. Second, because of the noble metal, the SPR effect is coming. The electrons are excited on the surface of noble metal. So they also enhance. And visible light active, then these metals are known as visible light active material, because the electrons can be excited by visible light. Now, what more could be done? Means there are a lot of things. By tuning the shape and size of those noble metals, we can prepare different kind of materials. And a range, we can use only one wavelength. We can use a range of wavelengths to excite this material, and especially visible light. So if we can use the visible light, it means we can use the sunlight. And then these photocatalytic things could be done in presence of sunlight. Okay, so see, the sunlight is available. So if anything could be done with the help of sunlight, that is really very useful. Like like solar cell, if we can prepare materials that can be activated in presence of sunlight, then it's very good. We don't need any extra source to activate our material. In the same way, if we use the graphene, so if you remember when we were discussing about the graphene, I told you the graphene, one of the best material for the electronic purpose. So in this, if we have the TiO2, we have noble metal, and we also add the graphene, then what will happen? The transport property of graphene, or we can say the graphene shows excellent transport properties. So what will happen again? The electrons available for photocatalysis, what they will do? The graphene will transport the electrons and it will not leave them to recombine with the holes. So, mean to say, by combining two or more materials, we can enhance the properties. For example, you can see here, like we have TiO2, even with the UV light, we can excite them, okay? And because of the Schottky effect or plasmonic effect, we'll have more and more number of electrons. And these electrons will be transported by graphene. So the reaction will be fast. And as soon as it will be irradiated with the light, more and more number of electrons will be available and they will not recombine back. And our whatever the things going on, the photocatalysis or any other application related to that, that will be very fast because of presence of these materials. So even if TiO2 is useful, but this functional nanomaterials are killing bacteria. Okay, I'm not going very in deep, but this is important to say here that TiO2 nanomaterials are used for antibacterial application under UV light, but using noble metals or any other combination like graphene or even the gold, that can be used without any irradiation because of the SPR, the surface plasmon resonance, they provide some heating properties and they also kill the bacteria. So these things are, I can say, a little bit deep research things, but if somebody is interested, they can learn about this. And you can see when TiO2 is there, the absorption in this visible range 400 to, we see this is called surface. So it shows the presence of gold. And because of this, we see the great enhancement in the photocatalytic degradation. This plot shows the enhancement in photocatalytic degradation. This is just the same kind of material and used in application of that in SCRS, surface enhanced Raman sensing application. This is also very important, and I need to discuss a little more here that if we have a combination of this metal oxide and noble metal, then this kind of combination could be used as a recyclable material. Why? Suppose we have noble metal on the surface and it gives SCRS sensing. Okay? Then what happens when we irradiate it with the UV light, it will degrade this material, this organic molecules. For that it was used as a sensing or sensor, we can say. Mean to say, if we have metal oxide and metal together, then using metal, we can detect the organic material, whatever is there, organic molecules, biological molecules, and using UV light on this metal oxide, we can degrade them. After degrade them, what will happen? The surface will be clean. Again, we can put the organic molecule and we can detect. And by UV, with the help of UV light, these metals can be degraded. So the surface can be clean. So these kind of materials could be used as a recyclable material. So the plasmonic photocatalyst. Now we have the plasmonic, means the plasmonic effect in metal nanoparticles and photocatalyst like TiO2 or any other semiconductor. So these are combinedly called as plasmonic photocatalyst. So this could be a good candidate for wastewater treatment, okay, for the detection of harmful organic materials or their degradation. So this is one of the best application we can say for the real societal application in the society, how we can use these materials. And work is going on this because you are not looking in this field. If you look, you will find there are something that is going on. This is again just an example. I can show you some of the results, like these are the TiO2 nanoparticles, and silver nanoparticles are just on the surface. So these are again UV visual spectra, photoluminescence. So these things are related to the photocatalytic activity. For the PhD students, it will be difficult to understand this part, but just to say that when we combine these two materials, we see the enhancement in sensing, okay, and in antibacterial activities. And also these materials are used in solar cells. So these are the different solar cells. Silicon-based solar cells, I already showed you, but there only silicon material is used. And here I wanted to say that these noble metal or TiO2-based composite materials are also being used in solar cells. So that was only one of the example for the silicon-based solar cell. These are the another solar cells where these materials are used. So overall, what we find from this lecture that these kind of materials, metal, noble metal, metal oxides, graphene, these are the functional nanomaterials, and these materials are like multifunctional because these are used in various fields, either field of energy, sensing, antibacterial, like light emitting diode, like we learned about the fluorescence. For kind attention and to listen me, and sorry for the interruption, it happened.
Now the webinar is open for all the participants for any questions, any small question.
Yes, please. It's important for especially for the PG students.
Any small question from the MSc students? Okay. As there is no further question from the students, now I would like to invite Dr. Rajesh Khatri, the head of the Department of Physics, for the votes of thanks. Now over to Rajesh Khatri.
Ji, Dr. Sir, good afternoon.
Good afternoon, sir.
Most welcome, Dr. Sir. On behalf of the Physics and the Chemistry Department and the principal of the college, I heartily welcome you for providing the right platform to share the knowledge of the nano materials with our students and their applications. How the things are changed, how the properties are changed when we move from covering good physics concept behind this. So I'm also thankful to my staff members, such a nice platform to connect with the students, and the students might have also learned something good about the new science, nanotechnology. And I'm also very much thankful to students also for giving their listening, sincere listening, even though there is some technology interference. So sorry for that also. So on behalf of DAV campus, I give the full credit to all the team for making this event beautiful and success. Thank you very much.
Students, please fill the feedback form for the e-certificates. That will be sent to the your Gmails. Kindly fill the.
मनोज
Yes,
जी
sir.
सर्टिफिकेट कल मिलेंगे बच्चों को
अच्छा कल मिलेंगे चलो फीडबैक फॉर्म जो सर ये भेज दो
फीडबैक भेज देते हैं
हाँ सर ये
करेंगे
हाँ जी सर ठीक है सर
हाँ, कोई नहीं भेज देते हैं
ओके सर थैंक यू
Thank
Okay,
you.
Manoj.
Thank you.
Okay, thank you very much.
Thanks, sir. Thank you, JP sir, for the valuable time you devoted to the students. Okay, sir.